Hello, I'm going to be learning C++ again. This time I will start with chapter 15. Wait, hold on. Um, so last stream I did chapter 14. I finished it, all of it. I think I took 3 hours. And I will try to complete chapter 15 this stream. So, so this is the code from last stream. This is the ball code from last stream. Anyways, the hidden this pointer and the member function chaining. One of the questions about classes that new programmers often ask is, when a member function is called, how does C++ keep track of which object it was called on? First, let's define a simple class to work with. This class encapsulates an integer value and provides some access functions to get and set that value. So, okay, there's an ID, there's a get and set function, and then there's a print function. Somehow when we call simple.setId, C++ knows that the function setId should operate on object simple. I mean, yeah, because you called it like this. And that MID actually refers to simple.mid. The answer is that C++ utilizes a hidden pointer named this. In this lesson, we will take a look at this in more detail. Inside every member function, the keyword this is a constant pointer that holds the address of the current implicit object. Most of the time we don't need this explicitly, but we can prove we can. But just to prove we can, so they're printing this MID. Is this a pointer? Like, does it store the pointer to the object? Oh yeah, it says here, use this pointer to access the implicit object. Note that print member functions from the prior two examples do exactly the same thing. It turns out that the former is shorthand for the latter. When we compile our programs, the compiler will implicitly prefix any member referencing the implicit object this. This helps our code more concise and prevents the redundancy from having to explicitly write this over and over. As a reminder, this operator actually does this. So it's the pointer. So this is the object itself. No, this stores the pointer to the object, and over here we dereferencing this, and then we are getting the ID. Although the call to function setId2 looks like it has only one argument, it actually has two. When compiled, the compiler writes the expression simple.setId2 as follows. So we have setId, and then we have the reference to the object. Note that this is now just a standard function call, and the object simple is now passed by address as an argument to the function. But that's only half of the answer. Since the function call now has an added argument, the member function definition also needs to be modified to accept and use this argument as a parameter. Here's our original member function definition for setId. How the compiler rewrites functions is an implementation specific detail, but the end result is something like this. Save static void setId. Then we have the object of simple, and then we are setting that object. Note that our setId function has a leftmost parameter named this, which is a constant pointer. Okay, so most of the time you won't need to explicitly reference this pointer. However, there are a few occasions where doing so can be useful. First, If you have a member function that has a parameter with the same name as a data member, you can disambiguate them by using this. So we have data, we have this data is data. Or like it's to separate the ambiguity. Oh, and the same thing works on struct as well. It can be useful to have a member function return the implicit object as a return value. The primary reason to do this is to allow member functions to be chained together so several member functions can be called on the same object in a single expression. This is called function chaining or method chaining. Consider this common example where you have where you are outputting several bits of text using stdcout. The first operator uses stdcout, the second and the string literal hello to print hello, comma to the console. However, since this is part of an expression, the extraction operator also needs to return a value. If this operator returns void, you will end up with this as the partially evaluated expression, which clearly doesn't make any sense. Instead, the extraction operator returns the stream output that was passed in, which in this case is stdcout. That way, after the first extraction operator has been evaluated, we get this. Oh, I see. So this returns this, so it can be reused again. Resetting a class back to default state. If your class has a default constructor, you may be interested in providing a way to return an existing object back to its default state. Although, as noted in previous lessons, constructors are only for initializations of new objects and should not be called directly. Doing so will result in unexpected behavior. The best way to reset a class back to a default state is to create a reset member function, which is like this. While you initialize a new object and override the implicit object. Here's a full program demonstrating this reset function. So mValue, what if mValue has a default value like 5? If we do this, what's going to happen then? For non-constant member functions, this is a constant pointer to a non-constant value. With const member functions, this is a constant pointer to a const value. So wait, for non-constant member functions, like this one, this is a constant pointer to a non-constant value. Oh, so this, what it's pointing at is a constant, so that cannot change. But the object is changeable. The object is non-constant. The object it's pointing at is a non-constant. If we add the constant keyword here, we are telling the compiler that the values inside the function are not going to be modified. Then this points to a constant object. It's treating the object as constant. The errors generated from attempting to call a non-constant member function on a constant object can be a little cryptic. When we call a non-constant member function on a constant object, the implicit this function parameter is a constant pointer to a non-constant object, but the argument has type constant pointer to a constant object. Converting a pointer to a constant object into a pointer to a non-constant object requires discarding the constant qualifier, which cannot be done implicitly. The compiler error generated by some compilers reflects the compiler complaining about being asked to perform such a conversion. Since the this pointer always points to the implicit object, you may be wondering why this is a pointer instead of a reference. The answer is simple. When this was added in C++, references didn't exist yet. If this were added in C++ today, it would undoubtedly be a reference. I will open the next chapter as well. So classes and header files. All of the classes that we have written so far have been simple enough that we have been able to implement the member functions directly inside the class definition itself. For example, here's a simple date class where all the member functions are defined inside the date class definition. So we have date, year, month, day. We have a constructor, a print constant, get year, get month, get day. However, as classes get longer and more complicated, having all member functions definitions inside the class can make the class harder to manage and work with. Using an already written class only requires understanding its public interface, not how the class works beneath the hood. The member function implements clutter up the public interface with details that aren't relevant to actually using the class. To help address this, C++ allows to separate the declaration portion of the class from the implementation portion by defining member functions outside of the function definition. Here's the same date class as above with the constructor and print member functions defined outside of the class definition. Note that the prototype for these member functions still exists inside the class definition, but the actual implementation has been moved outside. So date, a constructor definition. Also, we have a declaration here, a print declaration here. Can we move this outside as well? Member functions can be defined outside of the class definition just like non-member functions. The only difference is that we must prefix the member function names with the name of the class type. Okay, so date.print, constant, and then there's an implicit this over here. Note that we left the access function defined inside the class definition because access functions are typically only one line. Defining these functions inside the class definition adds minimum clutter, whereas moving them outside the class definition would result in many extra lines of code. For this reason, the definition of access functions are often left inside the class definition. If you define a class inside a source file, that class is only usable within that particular source file. Wouldn't it be the entire unit translation entire translation unit, because there may be other files that are like including the CPP file. In lesson 2.11, you learn that you can put functions declarations in a header file. Then you can include those functions declarations into multiple code files. Classes are no different. A class definition can be put in a header file and then included into any other files that want to use the class type. Naming your class header and code files. Most often, classes are defined in header files of the same name as the class, and any member functions defined outside of the class are put in the .cpp file of the same name as the class. Here's our date class again broken into .cpp and .h. So we have date.h, we have the declaration, year, month, day. And then we're including it here. Now that any other header or code file that wants to use the date class can simply include date.h. Doesn't defining a class in a header file violate the one definition rule if the header is included more than once? Types are exempt from the part of the one definition rule that says you can only have one definition per program. Therefore, there isn't an issue including class definitions into multiple translation units. Wait, we can have a different definition for types? What if like one file has one definition and another file has a completely different definition and then we are linking them? Including a class definition more than once in a single translation unit into a single translation unit is still an OTR violation. However, header cards will prevent this from happening. Types are exempt from part of the one definition rule that says you can only have one definition per program. So we can have a class definition in one translation unit and a completely different class definition in a different translation unit. Is that what they're saying? Inline member functions. Member functions are not exempt from the ODR. So you may be wondering how we avoid ODR violations when member functions are defined in the header. Member functions defined inside the class definition are implicitly inline. Inline functions are exempt from the one definition per program part of the one definition rule. Member functions defined outside of the class definition are not implicitly inline. This is why such functions are usually defined in a code file. Alternatively, member functions defined outside the class definition can be left inside the header file. If they're made inline, here's our date.h header again, with the member function defined outside of the class marked as inline. So we have this, and we have now inline. This date.h can be included into multiple translation units without issue. When they say type definition, when they say types are exempt, they mean only this part, right? So this can be in types are exempt from the one part of the one definition rule. Okay. Inline expansion of member functions. The compiler must be able to see a full definition of a function in order to perform the inline expansion. Most often such functions are defined inside the class definition. However, if you want to define a member function outside the class definition but still want to be eligible for inline expansion, you can define it as an inline function just below the class definition. That way, the definition of the function is accessible to anyone who includes the header. So why not put everything in a header file? You might be tempted to put all of the member function definitions into the header file. Okay. Either inside the class definition or as inline functions below the class definition. While this will compile, there are a couple of downsides. First, as mentioned above, defining members inside the class definition clutters up your class definition. Second, if you want if you change any of the code in the header, then you will need to recompile every file that includes that header. Mm, let me see. Okay, I think I understand. Wait, hold on. Let me just try. So we have this. And let me delete all this. And then add a header file. Let's call it date.h. And then how do we get rid of this pragma once over there? Is there a different file for classes? Like, are we supposed to code it differently in a Visual Studio? So let's say we have this. And then date.h, constructor definition. I don't like how this looks. And then what's their convention? They didn't like this, right? And then I should delete this. Date.h. What should I write in main? So why not put everything in the header file? First, as mentioned above, defining members inside the class definition clutters up your class definition. Second, if you want to change any of the code in the header, then you will need to recompile every file that includes that header. This can have a ripple effect. When one minor change causes the entire program to recompile, the cost of recompilation can vary significantly. If you change the code in a.cpp file, only that .cpp file needs to be recompiled. So if I make changes here, only this needs to be recompiled. And they're asking stdc out. Include iostream. But if I had this in the header, then everywhere that it's included will also have to be recompiled. Okay, this works. Hold on. Let's do something like add item a.cpp. Wait, where is the file? They say it already exists on disk. Never mind. Let's just do b.cpp. So x, and then void x. Like I want to see how it works in different translation units. And then z.cpp. And then I can call them directly, right? Because I'm linking them. So I can do like that. Would this work? Let's do 2060. No, I don't think this would work. I'll just make a declaration here. And I need to remove this. So we have two translation units here. One with z that date.h another one with x date.h. I think then we have another one with date.h iostream and date.cpp. This is a separate translation unit. And then main.cpp, this is a separate translation unit. So what they're saying is, if this was over in the .h file, if I made changes in the code, then if all of these would have to recompile. Like both x and z would have to recompile. Should I make a separate header for these two? Uh, testing.h. How do you do the like this? And then end if. Include testing.h. So now let's see what there's. Okay, I understood this. There are a few cases where it might make sense to violate the best practice for putting the class definition in the header and non-trivial member functions in the code. First, for a small class that is used only in one code file and not intended for general reuse, you may prefer to define the class directly in the single.cpp file. Second, if a class only has a small number of non-trivial member functions that are unlikely to change, creating a .cpp file that contains only one or two definitions may not be worth the effort. Thus, in modern C++, classes or libraries are increasingly distributed as header only, meaning all of the code for the class or library is placed in the header file. This is done primarily to make distributing and using such files easier, as header only needs to be included, whereas code file needs to be explicitly added to every project that uses it. So that can be complicated. So types are exempt from part of the one definition rule that says you can only have one definition per program. Therefore, there isn't an issue of including class definitions into multiple translation unit. So wait, if I didn't have the header guards, would this cause a problem? Because they are saying that types are exempt from the one definition rule. So if I'm defining this type in both x and z, and date as well. So wait, I don't understand. Okay, it's exempt, but what if I do this? So date.h is empty. No, include date.h. So x has date.h, but z has a different thing. Z has Z doesn't have this. Z has so one definition rule, and then get year doesn't get year returns the month. They all return the month. Now what? So you have different definition in different translation unit. So would the linker cause an error? It didn't. How does this work? Wait. Save date here, date, and then hold on. Date. Let's go to date.cpp, and then print constant this. It's constant. Anyways, let's see how this works. So does this like C++ does the compiler just ignore this? C out. So it's compiling Z. So const print already defined in date.object. Okay, so there won't be a linker error with the class, but there won't be would be a linker error with the individual function. So if I just declare it, then it would use the other definition of print. It would use this definition of print and m.year, m.month. No, it would use this definition of print m.year, m.month, m.day. But instead of that, I do get year, get month, get day. Get year, get a month, get day. Now, let's see. Let's see. So get year, get month, get day. In the definition of date here, get year, get month, get day returns month for all of them. But that's not what it did. Const D 2015. Hold on, let me see again. 2015, 1014. So does it like throw away this definition? But what happens if I do int m second, let's say, or hour, and then int m hour is 10. So it causes a linker error. I'm guessing like member functions have to be the same. Some member functions have to be the same. Wait. Notice that we have left access functions defined inside the class definition because access functions are typically one line. Oh yeah. Okay, I'm guessing some functions, they shouldn't be too much. There's like the, I think this overrides the other one maybe. We have date.h and we have date.h here. I think one must override the other. I think maybe that's how it works. I'm not really sure. Include. Default arguments for member functions. In lesson 11.5, we discussed the best practice for default arguments of member functions. If a member function has a forward declaration, especially one in a header file, put the default argument there. Otherwise, the default argument in the function definition. Because member functions are always declared or defined as part of the class definition, the best practice for member functions is actually simpler. Always put default arguments inside the class definition. Libraries. Throughout your program, you have used classes that are part of the standard library. The header files provide the declaration that the compiler requires in order to validate the programs you have written are syntactically correct. However, the implementations for the classes that belong to the C++ standard library are contained in a precompiled file that is linked in automatically at the link stage. You will never see the code. Many open source software packages provide both .h and .cpp files for you to compile into your program. However, most commercial libraries provide only .h and a precompiled library file. There are several reasons for this. It's faster to link a precompiled library than to recompile it every time you need it. A single copy of a precompiled library can be shared by many applications. And then third is intellectual property reasons. You don't want people stealing your code. So ht.reader. What is the purpose of defining member functions outside the class definition? So to make the class definition stronger and easy to manage, to separate the public interface from the implementation when defined in a source file, to minimize recompilation times. How do you define a member function outside the class definition? Define the function with a class name prefix using the scope resolution operator. So they're referring to this. When should trivial member functions be defined inside the class definition? When should trivial member functions be defined inside the class definition? When the functions have a single line of code. So I'm guessing for these ones, there's no point putting in the .cpp file because it's only one line. Where should the class definition be placed to facilitate reuse in multiple files or projects? In a separate header file with the same name as the class. Which of the following is true about one definition rule for classes and member functions? Member functions defined inside the class definition are implicitly inline. Oh, so that's why it was causing the error. Because the definition has to be the same across. But wait, hold on. When I was changing get year, get month, get day, why didn't it cause an error? and thus exam from the one definition rule. Wait, what was this? 5.2. I should be reading 5.3. So a nested type, consider the following short program. We have enum class fruit type. Then we have class fruit. There's nothing wrong with this program, but because enum class fruit type is meant to be used in conjunction with the fruit class, having it exist independently of the class leaves us to infer how they're connected. So m dot type, m percentage eaten. So where is fruit type is used here? So far we have seen class types with two different kinds of members, data members and member functions. Our fruit class is the example above. Our fruit class in the example above has both of these. Class types support another kind of member, nested types, also called member types. Class types support another kind of member, nested types, also called member types. To create nested type, you simply define the type inside the class. So enum type. So this entire enum is part of fruit. There are a few things worth pointing out here. First, note that fruit type is now defined inside the class where it has been renamed type. Second, nested type has been defined at the top of the class. Nested type names must be fully defined before they can be used. Third, nested types follow normal access rule. Uh, Type is defined under the public access specifier. Fourth, class types act as a scope region for names declared within, just as the namespace do. Therefore, the fully qualified name of type is fruit colon type, and the fully qualified name of the apple enumerator is fruit colon apple. Oh, so the class keyword makes its own namespace as well, like it makes its own scope. Within members of the class, we do not need the fully qualified name. Okay, so they did m type. They're checking if whether the type is cherry, and instead of doing fruit colon cherry, they're just using cherry, just like that. Finally, we changed our enumerated type from scoped to unscoped. Since the class itself is now acting as a scope region, it's somewhat redundant to use scoped enumerator as well. Otherwise, they would have to type fruit colon type colon apple. Class types can also contain nested type def or type aliases. Note that inside the class, we can just use ID type. Wait, what are they doing? Nested type defs and type aliases. So where is the alias being used? Oh, using ID type int. Oh, so this ID type is only, we can only use it inside employee. Outside of the class, we must fully use the qualified name employee .id type. We discuss the benefits of type aliases in lesson 10.7. Nested classes and access to outside class members. It's fairly uncommon for classes to have other classes as a nested type, but it is possible. In C++, a nested class does not have access to the this parameter pointer of the outer containing class. So nested classes can not directly access members of the outer class. This is because nested classes can be instantiated independently of the outer class. However, because nested classes are members of the outer class, they can access any private members of the outer class that are in scope. So ID pointer, ID, you have class printer, you have a class inside a class, public void print, and they have to pass the employee as a argument because they can't access the outside containing class. So employee colon printer p and then p dot print John. But can the outside class access print? Nested types and forward declaration. A nested type can be forward declared within a class that encloses it. So this is forward declared. This is the definition of forward declared type. This is inner2 is forward declared. And then the definition is here. A nested type cannot be forward declared prior to the definition of the enclosing class. So class outer, inner. Okay, we cannot do this. But we can do this. We can't forward declare nested types before the containing class. Introduction to the destructors. The cleanup problem. Let's say that you are writing a program that needs to send some data over a network. However, establishing a connection to the server is expensive, so you want to collect a bunch of data and then send it all at once. Such a class might be structured like this. So we have network data, private server name, data queue, then public network data, add data, send data. So add data, and then send data. However, this network data has potential issues. It relies on send data being explicitly called before the program is shut down. If the user of the network data forgets to do this, the data will not be sent to the server. If some condition, return false. If the user of the network data forgets to do this, the data will not be sent to the server and will be lost when the program exits. Now you might want to say, well, it's not hard to remember to do this. And in this particular case, you're right. But consider a slightly complex example like this function. In this case, if some condition is true, then the function will return early and send data will not be called. To generalize this issue, classes that use a resource often need to be explicitly sent or closed before the class object using them is destroyed. In other cases, we may want to do some record keeping prior to the destruction of the object, such as writing information to a log file or sending a piece of telemetry to a server. The term cleanup is often used to refer to a set of tasks that a class must perform before an object of the class is destroyed. Destructors to the rescue. Classes have another type of special member function that is automatically that is called automatically when an object of a non-aggregate class type is destroyed. This function is called a destructor. Destructors are designed to allow a class to do any necessary cleanup before an object of the class is destroyed. Like constructors, destructors have specific naming rules. The destructors must have the same name as the class preceded by how do you pronounce this? Tiled. It cannot take arguments and it has no return type. So here's our destructor. So destructing simple ID. Destructors may safely call other member functions since the object isn't destroyed until after the destructor executes. So when simple one dies here, we are calling out destructing simple ID. Improving the network data program. Back to our example at the top of the lesson, we can remove the need for the user to explicitly call send data by having a destructor call that function. So when it's destroyed, it sends the data. An implicit destructor. If a non-aggregate class type object has no declared destructor, the compiler will generate a destructor with an empty body. This destructor is called an implicit destructor and is effectively a placeholder. A warning about stdexit function. In lesson 8.12 halts, we discussed the stdexit function can be used to terminate your program immediately. When the program is terminated immediately, the program just ends. Local variables are not destroyed first, and because of this, no destructors will be called. Be wary if you're relying on your destructors to do necessary cleanup work in such a case. Class templates with member functions. Class templates with member functions. In lesson 11.6, we took a look at function templates. So we have template type in empty. With a function template, we can define template parameter type name t and then use them as a type of our function parameter. Lesson 13.13, we covered class templates, which allows us to use type template parameters for the type of our data members of the class type. So template t and then pair. Type template parameters in member functions. Type template parameters defined as part of the class template parameter declaration can be used both as a type of the data members and as a type of the member function parameters. So pair using a type template t here, and then similarly t is being used here. We can because our class data members are of type t, we can make the parameters of a constructor type const t reference. So reference. So this is a reference to the variable. So the user can supply initialization values of the same type. Because t might be expensive to copy, it's safer to pass by const reference than by value. Second, we don't need deduction guides for CTAD to work with non-aggregate classes. A matching constructor provides the compiler with the information it needs to deduce the template parameters from the initializer. In a prior lesson, we noted that the name of a constructor must match the name of the class. But in our class template for pair t above, we named our constructor pair and not pair t. So we named it pair. Oh, over here they named it pair T. Within the scope of a class, the unqualified name of the class is called an injected class name. In a class template, the injected class name serves as a shorthand for a fully templated name. Because pair is the injected class name of pair T within the scope of our pair T class template, any use of pair will be treated as if it had been as if we had written pair T instead. Therefore, although we named the constructor pair, the compiler treats it as we have written pair T instead. The names now match. Note that the parameter has type T, not pair T. Let me see. It's template T, pair. This is T, this is T, this is a reference to T. And then in the asql function, we use this. Way to define member functions for class templates outside the class. With member functions for class templates, the compiler needs to see both the class definition and the template member function definition. Therefore, we typically want to define both a class and its member function template inside the same location. When a member function template is defined inside the class definition, the template member function definition is part of the class definition. So anywhere the class definition can be seen, the template member function definition can also be seen. This makes things easy. When a member function template is defined outside the class definition, it should generally be defined immediately before the class definition. That way, anyway, the class definition can be seen. The member function template definition immediately below the class definition will also be seen. In the typical case where a class is defined in the header file, this means any member function template defined outside the class should also be defined in the same header file below the class definition. So write a class template named triad that has 3 private data members with independent type template parameters. So okay, uh, the following program should work. IOStream. This should not be here. This should be here. Let's see. Write a class template named triad that has 3 private data members with independent type template parameters. The class should have a constructor access function and a print member function that is defined outside of the class. So class triad we have template T, template type name T, let's see, and then private we have uh, first first second third. And then we have the construct triad. How do we do the constructor? Const reference f second, third, and then this is m first, f m second, s m third, d, and then void triad. We do it like this. No, wait, hold on. Type first, second, third. There are three types here. Three different types here. Second, third, and then first, second, first, second. If we have multiple type names, do we do it like this, or do we write type name before each of them? I can't remember. So we have print. Hold on. So we have constant triad, constant reference to triad, triad reference d, and then print void. Is this correct? Constant d pair. What else is left? So std cout, std cout, let's see, std cout. We have this as one character. And then wait. Oh yeah, we need a getter and setter function. So if get first, return m first, second, third. I don't know if I'm doing it this correctly. Second, third. How do you get rid of this menu, this suggestion menu? And then we do get first. Is it t dot? Hold on. How do you do this? Pair dot m first. Pair dot m second. So this should work, right? First. Why is this not working? Triad. Yeah, print triad. Is it like this? Type name. Type name. Constant. And then the reference. T dot. Okay, let's just write it like this. And then I'll just. I'm not concerned with formatting right now. T dot get third. Let's see if there is any error. I think this is written like this. Yeah. And uh, I don't know how well this works. But let's see. Do they need the setter function as well? First is not a member of triad. What do they mean? Triad function does not take 0 arguments. Print. Oh, wait. Uh, t1 dot print. I just need to do this, right? And then I need to remove this here. Let's see what the error is. First is not a member of triad. Line 37. Top first. We need Wait, I think we have to rename the access function. We need to rename this to first, second, and then third. First, second, and then third. How well does this work? So error 40 and 6. It has problem with print. Cannot convert this pointer from constant triad in double string to constant double in triad string reference. So they have a problem with the print statement. Let me see the answer. And case their TOV constant. Wait, hold on. Okay, and then over here they need a. Should it be constant? They're not changing it, right? Oh no, constant reference means like what it's referring to doesn't change. Let's see. Void triad int double std string print void cannot convert this to that. Okay, how do they deal with print? Print const. Shouldn't they all be const? Yeah, they are all const. But why doesn't this work? Void triad. It can't work for some reason. Okay, if anyone can tell me why the const work and without const didn't. Std slash n. This is what it wanted to print, right? Why is this C? Oh, I think in the print function, it's not. There's not supposed to be any new line. Maybe. Yeah, they did not have any new line in the print. If we remove const from the print function declaration definition, the program will no longer compile. Why not? T2 is a constant object. Oh, I see this here. Oh, that's why it didn't work here, but it worked here. So only constant member only constant member functions can be invoked on T2. If we make print a non-constant member function, then T2 is not allowed to call it. This is because a non-constant member function could conceivably modify the implicit object, which would be a violation. Six, chapter 7. So, int generate ID. Just like how it's static with functions, I think it's the same thing with classes. It belongs to the class. Before you go into the static keyword as applied to member variables, first consider the following class. When you instantiate a class object, each object gets its own copy of the normal member variables. Uh, Unlike normal member variables, static member variables are shared by all objects of the class. Okay. Static members are not associated with class objects. Although you can access static members through objects of the class, static members exist even if no objects of the class have been instantiated. This makes sense. They're created at the start of the program and destroyed at the end of the program. Is the scope of the static global even if they're within a function? Uh, Essentially, they are global. Static members are global variables that live inside the scope of region of the class. There is little difference between a static member of a class and a normal variable inside a namespace. So we have as a static value. We access it like this using the class name. Defining and initializing static member variables. When we declare a static member variable inside a class type, we are telling the compiler about the existence of a static member variable, but not actually defining it. Because static member variables are essentially global variables, you must explicitly define the static member outside of the class in the global scope. Is there no default for the initial value for? No, I mean like the initial value for static inside the class, like over here. We can't provide an initial value. This line serves two purposes. Instantiates the static member variable. In this case, we are providing the initial value 1. If no initializer is provided, these static member variable are 0 initialized by default. Note that this static member definition is not subject to access control. You can define and initialize the value even if it's declared as private. For non-template classes, if the class is defined in a header file, the static member definition is usually placed in the associated code file for the class. Alternatively, the member can also be defined as inline and placed below the class definition in the header. If the class is defined in a source file, the static member definition is usually placed underneath the class. Do not put static member definition in a header file. Much like a global variable, if that header file gets included more than once, you will end up with multiple definitions. For template classes, the templated static member definition is typically placed underneath the template class definition in the header file. Initialization of a static member variable inside the class definition. When the static member is a constant integral type or a constant enum, the static member can be initialized inside the class definition. We introduce inline variables, which are variables that are allowed to have multiple definition. C++17 allows static members to be inline variables. Such variables can be initialized inside the class definition regardless of whether they are constant or not. This is the preferred method of defining and initializing static members. Because constant expression members are implicitly inline, static constant expression members can also be initialized inside the class definition without the explicit use of the inline keyword. So static constant expression. An example of static member variables. Why use static variables inside the class? One uses to assign a unique ID to every instance of the class. Here's an example. So static in I don't get the use of the inline word. Static variable. Isn't static already global? So it's defined everywhere. Or maybe I think if you have a header file with class something, and that something is going into multiple files, then you have the same definition for ID generator. That's what I'm guessing this inline is for. So ID generator, every time you construct, the ID is incremented. Int get ID constant return MID. Only static members may use type deduction. A static member may use auto reduce its type from the initializer or a class template argument deduction to reduce the template type arguments from the initializer. The reason for non-static members may not use auto or ctad. The reasons for this distinction being made are quite complicated, but boil down to there being certain cases that can occur with non-static members that lead to ambiguity or non-intuitive results. This does not occur for static members. Thus, non-static members are restricted from using these features, whereas static members are not. Auto allowed, not allowed for non-static members, auto allowed for static members. So we have 6 and then chapter 7. Static member functions. In the previous lesson, you learned that static member variables are member variables that belong to the class rather than objects of the class. If a static member variable is made public, it can be accessed directly using the class name and the scope resolution operator. So something like this. Or what if it's private? Consider the following. So this will cause an error because it's private. In this case, we can't access the static member directly from main because it is private. Normally, we can access private members through public member functions. While we could create a normal public member function to access s.value, we would then need to instantiate an object of the class type to use the function. Okay, so they're making an object of s, and the object is being used here. Member variables aren't the only type of members that can be made static. Member functions can be made static as well. So here's a static function. Can there be private function in classes? Static member functions have no this pointer. That makes sense. Static members defined outside of the class definition. Uh, this works the same way as normal member functions. So int id generator colon get next id is defined here. As noted in 15.2, member functions defined inside the class definition are implicitly inline. Member functions defined outside the class definition are not implicitly inline but can be made inline using the inline keyword. A word of warning about classes with all static members. Be careful when writing classes with all static members. Although such pure static classes can be useful, they can come with potential downsides. First, because all static members are instantiated only once, there is no way to have multiple copies of this class. Second, in the lesson on global variables, you learn that global variables are dangerous because any piece of code can change the value of the global variable and end up breaking another piece of seemingly unrelated code. The same holds true for pure static class. Or what if all the static variables are private? Pure static classes versus namespaces. Pure static classes have a lot of overlap with namespaces. Uh, One significant difference is that classes have access control while namespaces do not. In general, it is preferable when you have static data members and don't need access control. C++ does not support static constructors. While some modern languages do support static constructors for wait, if you if you can initialize normal member variables via constructor, then by extension it makes sense that you should be able to initialize static member variables via static constructor. And while some modern languages do support static constructors for precisely this purpose, C++ is unfortunately not one of them. If your static variable can be directly initialized, no constructor is needed. Okay. You can initialize the static member variable at the point of definition. We do this in the ID generated example above. If initializing your static member variable requires executing code, there are many different and somewhat obtuse ways of doing this. One way that works with all variables, static or not, is to use a function to create an object, fill in with data, and return it to the caller. This return value can be copied into the object being initialized. So we generated this, and then we are assigning it here. Convert the random namespace in the following example to a class with static members. So I guess this would be static. Yeah, the generated function is static. Hold on. This is static, and then this is static, and what's this? Empty generates a seeded and copies it into our global object. Okay. Friend, non-member functions. Much of this chapter and last we have been preaching the virtues of access control, which provide a mechanism for controlling who can access the various members of a class. Private members can only be accessed by other members of the class, and public members can be accessed by everyone. Uh, there are situations where this arrangement is either not sufficient or not ideal. Consider a storage class that is focused on managing some set of data. Now, let's say you want to display that data, but the code that handles the display will have lots of options and is therefore complex. You could put the storage management functions and the display management functions in the same class, but that would clutter things up and make for a complex interface. You could also keep them separate. The storage class manages storage and some other display class manages all the display capabilities. That creates a nice separation of responsibilities. But the display class would then be unable to access the private members of the storage class and might not be able to do its job. Alternatively, there are cases where syntactically we might prefer to use a non-member function over a member function. This is commonly the case when overloading operators. Inside a body of a class, a friend declaration using a friend keyword can be used to tell the compiler that some other class or function is now a friend. In C++, a friend is a class or function that has been granted full access to the private and protected members of another class. In this way, a class can successively give other classes or functions full access to their members without impacting anything else. Okay, I want to see like an example. So accumulator, private, public, and then we have friend, void print. Here is a friend declaration that makes non-member function void print a friend of accumulator. Because print is a friend of accumulator, it can access the private members of accumulator. So you have a function that is not a member, and this function is able to use the private keywords of accumulator. Defining a friend non-member inside a class, much like member functions, can be defined inside a class if desired. Okay. Friend non-member functions can also be defined inside a class. The following example defines friend non-member function print inside the accumulator class. So we have ACC add 5. Then we have print. Friend functions defined inside a class are non-member functions. Oh, I see. But what's the point of putting them inside? Oh, I mean, yeah, they can access the private variable. Syntactically profiling a friend non-member class. We mentioned that there are times we might prefer to use a non-member function over a member function. Let's show an example of that now. So we have value with a private value and then explicit value. I forgot what the explicit keyword does. And then boolean, and then we have friend is equal to non-member. So boolean value is equal to member. We're defining it here, and then boolean is equal to non-member. We are defining it here. So this is a case where you might prefer a non-member over a member function. In is equal to non-member, both objects are passed explicitly. This leads to better parallelism in the implementation of the function, as m value member is always explicitly prefixed with an explicit parameter. As the m value member is always explicitly prefixed with an explicit parameter. Okay. But why are we saying is equal to non-member? You may still prefer the calling syntax is equal to member over is equal to non-member, but when we cover operator overloading, we will see this topic come up again. A function can be a friend of more than one class at the same time. For example, consider the following example. So class humidity, class temperature. Your friend void print weather, and then print weather is defined here. So a function can be friend of more than one class at a time. So it can access the values of both humidity and temperature. Doesn't friendship violate the principle of data hiding? No, friendship is granted by the class doing the data hiding with the expectation that the friend will access its private members. Think of a friend as an extension of the class itself with all the same access rights. As such, access is expected, not a violation. Prefer non-friend functions to friend functions. In the following example, if the implementation of accumulator is changed, the implementation of print will need to be changed as well. So accumulator, need to modify this. And if we rename this, we will have to modify this. So that's why it's better to make this a member. Be cautious when adding new members to the public interface of an existing class, as every function adds some level of clutter and complexity. In the case of accumulator above, it's totally reasonable to have an access function to get the current accumulated value. This is 15.8, right? I need 15.9 and 10 as well. Friend classes and friend member function. A friend class is a class that can access the private and protected members of another class. Here's an example. Because the display class is a friend of storage. So we have storage, the constructor, and a friend. And then we have class display. And then display storage. We can access the private values of storage. Display members can access the private members of any storage object they have access to. First, even though display is a friend of storage, display has no access to this pointer of the storage object. Friendship is not a reciprocal just because display is a friend of storage. Just because display is a friend of storage does not mean storage is also a friend of display. So it's a one-way friendship. Friend member functions. Instead of making an entire class a friend, you can make a single member function a friend. This is done similarly to making a non-member function a friend, except the name of the member function is used instead. However, in actuality, this can be a little trickier than expected. Let's convert the previous example to make display storage a friend member function. So class display, forward declaration for class display storage. Then we have friend void display storage. Only one member function can access the private values. So display storage, this can access the private values. However, it turns out this won't work. In order to make a single member function a friend, the compiler has to have seen the full definition for the class of the friend member function. Since class storage hasn't seen the full definition for class display yet, the compiler will error at the point where we try to make the member function a friend. Fortunately, this is easily resolved by moving the definition of class display before the definition of class storage. However, we now have another problem. Because member function display storage uses storage as a reference parameter, and we just move the definition of storage below the definition of display, the compiler will complain that it doesn't know where storage is. Okay, there was the other solution then. So forward declare class storage, or since the whole class is being mentioned, we can forward declare for storage here, and then we can define it later. Okay, what's this? In geometry, a point is a position in space. We can define a point in a 3D space as a set of coordinates x, y, z. For example, point 2, 1, 0 would be the point at coordinate x is 2, y is 1, and z is 0. In physics, a vector is a quantity that has a magnitude and a direction, but we can define a vector in a 3D space as well. A vector can be applied to a point to move a point to a new position. And this is done by adding the vector's direction to the point position to yield a new position. Such points and vectors are often used in computer graphics. Given the following program, vector 3D, class point 3D, make point 3D a friend class of vector 3D and implement function point 3D move by vector. Hold on. I need all of this. So we have vector 3D, point 3D, and main. So void move by vector, implement this function as a friend of class vector 3D. So vector 3D, so I need to access these variables. So point 3D, m underscore x plus equals to v dot m underscore x, and then hold on. Let me think how I can do this. I have an idea. We can make this a friend. So point 3D move by vector void, right? But it's not defined. However, you can put this here and then define it later. Void point 3D move by vector. And then we do mx is equal to v dot mx y y, and then same thing for z. And then let's see if this works. Make point 3D a friend class of vector 3D. They said make this function a friend class. Do I have to make the whole class a friend? Friend class point 3D, but point 3D is not defined, right? I mean, it's not declared. Instead of making class point 3D a friend, make the member class a friend of vector 3D. Void print vector cannot convert argument 1. Cannot convert argument 1 from vector 3D to constant integer. This is line 45. We vector we have void moved by vector 3D. Why does it say integer? And what's this over here? Why do they need this? Oh, never mind. So we're printing the point. I don't get what the error is. Hold on. Vector 3D. Okay, I understand how this works. First, we need to tell the compiler that class named vector 3D exists. And then, hold on. Class vector 3D. So it knows vector 3D exists, and then it can use vector 3D here. And then vector 3D knows this function exists, which is a friend. So 1, 2, 3, 2, 2 minus 3. Hold on, no. It has to be plus. Oh, and now they're separating it. Okay, now the addition is done. You implement the solution to the prior step using 5 separate files. And then, okay. Point 3ddh, point 3d cpp, vector 3dh, vector 3d cpp, and main.cpp. Okay, so they're defining this. forward declaration, so it can be used here. Then injector 3d.h. Sorry, this is point 3d.cpp. Yeah, they're implementing everything. The vector 3d.h. In this, we discussed how calling access functions that return references to data members can be dangerous when implicit objects is an R value. Here's a recap. So getting returns by constant reference. So case 1, okay, use returned reference to member of R value class object in same expression. Create employee Frank, get name. So it's being used in the same expression. But save return reference to a member of R value class object for use later. It's undefined behavior because get name is it returns the reference, but the return value is destroyed. In case 2, the R value object returned by create employee carbo is destroyed after initializing ref, leaving ref referencing a data member that was destroyed. Subsequent use of ref exhibits undefined behavior. This presents somewhat a conundrum. If our getName function returns by value, this is safe when our implicit object is an R value. When our getName function returns by constant reference, this is efficient, but can be misused when the implicit object is an R value. Since member functions are typically called on L-value implicit objects, the conventional choice is to return by constant reference and simply avoid misusing the return reference in cases where the implicit object is an R value. The root of the challenge illustrated above is that we only want one function to service two different cases. What's optimal for one case isn't ideal for the other case. To help address such issues, C++11 introduces a little known feature called a ref qualifier that allows us to overload a member function based on whether it is being called on an L value or an R value implicit object. Using this feature, we can create two versions of getName, one for the case where our implicit object is an L value and one for the case where our implicit object is an R value. So capable of being called both by an L value and R value. Over here, qualify overloads function to match only L value implicit objects. And if it's double ampersand, it matches with only R values. So it returns by value. Hold on. When you're returning this by reference, reference becomes tangling when return value of create employee is destroyed. So create employee carbo, we are doing get name, but then this employee gets destroyed. Okay, yeah, that makes sense. The above R value overload of getName is potentially suboptimal from the performance perspective when the implicit object is a non-constant temporary. In such cases, the implicit object is going to die at the end of the expression anyway. So instead of having the R value getter return a possibly expensive copy, we can have it try to move the member. We can have it try to move the member using std move. Okay, we haven't done move yet. While left qualifiers are neat, there are some downsides to using them in this way. Adding R value overloads to every getter that returns a reference adds clutter to the class. Having an R value overload returned by value means we have to pay for the cost of copy. Additionally, most C++ developers are not aware of these features. The standard library typically does not make use of this feature. Okay, let's just read the summary and then I will end the stream. So this keyword reference in order to enable method chaining. If several member functions can be called on the same object in a single expression. A type that is defined inside a class is called a nested type. Type aliases can also be nested. Should I do the quiz? Let's create a random monster generation. First, let's create a scoped enumeration of monster type named monster type. Include the following monster type. Okay, I mean, I saw the solution. I will just include it anyways. Now let's create our monster class. So you have this type. And then now let's create our monster class. Our monster class will have 4 attributes. A type, monster type, a name, a roar, and the number of hit points. So we have a class monster. We will put this inside. And then this is private, right? Private. Our monster will have 4 attributes. A monster type, a name. So monster type, right? And then I need to include string. Include string. Wait, I forgot. Was it string.h or string? std. I think it was just string. I can't remember. Okay, anyways, std string name, and then we have integer health, std string roar, and then integer health. enum class monster. Enum class is specific to monster, so make monster type a nested unscoped enum. Now we have type. Let's just. I think let's just leave it to monster type. And wait, are enums private? No, they're public. Let's just put this in public then. And yeah, then maybe we have public again. Monster type, and then name. Question mark, and then health. Create a constructor that allows to initialize all of the member variables. So this should work. Public monster skeleton. So we have monster. We have monster type D. And then we have std string name, and then std string again, roar, and then int health. So type is now D. Why does it do this? Name is now N. Wait, hold on. And then roar is now R, and health is now H, and let's call this H. So is that what they did? They're using string view instead of string. I'll just do that then. Let's just do m underscore. Now we want to be able to print our monster so we can validate that it's correct. Bones, the skeleton has 4 hit points and says rattle. Enables the vampire is dead. So void print. Do we need the print to be outside? Yes, I think it's better if it's just here. So print std cout. underscore name has underscore health health has for health uh, m dot type name has for health and says m dot row. So this let's just separate it like this. This is if m dot health else std out m dot type m underscore name is dead. Let's copy this. Let's see. So we missed this. So 4 bonds has 4 health and says rattles. 6 nibbles is dead. Wait, what? No, it should be m name. Do I need to use a switch keyword? Or can I like assign the enums a string? We have to use switch. So we have this. Return Skeleton bones has 4 heads and 6 rattles. Vampire Nibbles is dead. It's better if I add a full stop here. Now we can create a random monster generator. Let's consider how our monster generator will work. Ideally, we'll ask it to give a monster and it will create a random one for us. Because monster generator does not have any state, this is a good candidate for a namespace. In monster generator namespace, create function within generator. This should return a monster. For now, make it return monster, skeleton, bones, rattle, and 4. Are they just incrementing it? How are they doing the generator? So monster generator. Okay, but how are they? Add 2 more functions to monster generator namespace. Get name will take a number between 0 and 5 inclusive and return a name of your choice. Get roar will take a number from between 0 and 5 and return a roar of your choice. So let's see what they did. Get type string, get name between 0 and 5, get roar between 0 and 5. Wait, 5, but there are many monster types, right? Why only 0 to 5? Now we will randomize our generated monster. Or they're using random.h. That's how they're generating a random one. So generate random.get. Oh, I see. Okay, I will end the stream here then. Next stream, I would most likely do math, the calculus 3, and yeah, I'll see you guys next time.